So one of the things is that it's really time consuming to draw molecules in three-dimensional shape shown for the enantiomers, like we've got here for L and D glyceraldehyde. But there's a way to represent these mirror images in 2 dimensions. Emil Fischer was a German chemist, and he worked a lot with carbohydrate chemistry, and he introduced a method in the late 19th century. And so basically these are Fischer projections. And when we talk about a Fischer projection, this is just the 3D shape for chiral molecules with the chiral carbon represented at the intersection of 2 lines. So what we see here is this carbon, and now that carbon is right here where we have the line here. So now we've just got a line showing that carbon. In the Fischer projection, that chiral carbon is represented by the intersection of those 2 lines. If the compound is a carbohydrate, the carbonyl group is placed at or near the top. So you're going to place the carbonyl group at or near the top. Now, I want to emphasize something here. When you look at Fischer projections, it's not guaranteed that every one of these is going to be a chiral center. So you still have to check and make sure that there are 4 groups that are attached. Now, when we look at this, right, this is, when you place it this way, the molecule is positioned so the 2 bonds coming towards you out of the plane of the paper right here are drawn horizontally right here in the Fischer projection, and then the 2 bonds projecting away from you into the plane of the paper here and here are drawn vertically. When you see a Fischer projection, you have to make the connection between the Fischer projection here and the 3D molecule here. So again, when we do this, right, the horizontal bonds are pointing toward you, and then the vertical bonds are pointing away. From you. I like to think of this like a little bow tie, where when we look at it this way, if you think about a bow tie kind of like points out, you know, like, so if that's somebody's neck right here, a bow tie is coming out towards you. And so those vertical bonds are pointing towards you. That's how I like to remember it. Use that if it works, ignore it if it doesn't, but hopefully it will help as well. Now, there's another way that we can designate these Fischer projections, or one of the things that Fischer projections help us with is to differentiate between the 2 enantiomers. When you have the carbonyl group at the top and we've got our 2 enantiomers here, we know that these are 2 enantiomers, but we need to name them differently. We use the D and the L designation here. And so how you do this is you find the chiral carbon that's closest to the bottom. And so we're going to look at the chiral carbons here, right? And what we're looking for here is if the functional group, which the functional group here in this case is an OH, is on the left side, right, then it gets the L designation. If the functional group which is the OH is on the right side, it gets the D designation. So when we identify the chiral carbon that's closest to the bottom or farthest away from the carbonyl, and we look and we see here that this OH is on the right side, that's D. Here, the OH is on the left side, and that's L. And that's how we can classify or tell the difference between these through words. Now, we don't just do this for carbohydrates. We also are going to do this when we classify amino acids. And so let's do an example. This asks us to draw the Fischer projection for the D and L forms of the following. And alanine is an amino acid, and we're going to talk about these in the protein chapter. So when we set this up, we are going to look here and we're going to say, all right, this carbon here is our chiral carbon. It's bonded to 4 different things. And so now that's going to be that little asterisk there. We are going to arrange this so that the carbonyl group, that C double bond O, OH, is at the top, and then I am going to put a CH3 here at the bottom, and then we are going to put the H and the NH2 on the other 2 sides. Then to draw the other form, we keep the carbonyl group there, okay, and all we do is we switch these 2 groups here. Now, this is a relatively small molecule, and so we only have 1 chiral carbon, so we're gonna pick, so it's the chiral carbon that's farthest away from that carbonyl group. So we've got this chiral carbon that we're looking at, and we're looking at the functional group. And we see in this structure, the functional group here is on the right side, and in this structure, the functional group is on the left side. So if the functional group is on the right side, then that is D alanine. And so when we name it, we use a D and then we put a dash. And then when it's on the left side, that's L alanine. And so again, we're looking for the functional groups. In carbohydrates, this is going to be OH, and in amino acids, it's going to be the NH2 group there. Now, the reason that we talk a lot about this is because the physical properties of the 2 compounds that make up that pair of D and L isomers are generally the same, but there is an exception, and that's the way solutions of these compounds are affected by polarized light that is passed through them. So let's just put some words to that. So the physical properties of D and L isomers are generally the same, right? And D and L, but D and L isomers rotate in different directions in plane polarized light. So let's talk about what plane polarized light is first. Ordinary light just kind of points in all different directions, and when we say all different directions, we mean all different planes. And so that's put through a polarizing lens. This would be a lens like that would be really similar to sunglasses if you've ever worn polarized sunglasses, or if you are interested in photography and use a polarizing lens. And what this does is that it filters out any of the light that's going in a direction other than the filter. And so only light comes through that's going in one direction. Then what happens is there's a tube containing a solution of the enantiomer, and as the light goes through, the tube is rotated, and the rotated plane polarized light is what is detected. And it rotates in one direction for one enantiomer and another direction for the other enantiomer. And so we give some names to this, and one of the names that we talk about here is levo rotary, right? And this is the enantiomer that rotates plane polarized light to the left. And then we also designate this as the negative enantiomer. Okay. You can also have dextrorotary, and this is the enantiomer that rotates the plane polarized light to the right. And this is the positive enantiomer. Okay. And so some synonyms there for how we're going to refer to these. Now, one of the things that's really, really important here is the D and L designations for the naming that we just went over have nothing to do with let's pretend like I spelled that right. Sorry about that. Dextrorotary or levo rotary, right? But only these D and L only relate to the Fischer projections. They have nothing to do with plane polarized light. So you could have one D enantiomer that rotates positive, right? And then you can have another D enantiomer of another molecule that rotates negative. So that has nothing to do with it one way or the other. Now, this is the way these rotate in plane polarized light is called optical activity. So when we talk about optical activity, this is just the property of rotating in plane polarized light. And then if you have an optically active molecule, right? This just refers to a molecule that will rotate in plane polarized light. And if it rotates in plane polarized light, it's just one enantiomer or the other. Okay. Now, why is this important? Okay. So why is chirality important for the study of biomolecules? Well, that reason stems from the fact that living organisms, both plant and animal, consist largely of chiral substances. So, most of the compounds in natural systems, including biomolecules like carbohydrates and amino acids, are chiral. So, carbohydrates and amino acids, which we're going to talk about in the protein chapter. And although these molecules can, in principle, exist as a mixture of stereoisomers, quite often only one stereoisomer is found in nature. Now, this isn't always the case. In some instances, two enantiomers are found in nature, but they're not found together in the same biological systems. So, for example, when we have lactic acid, it occurs in both the natural forms, and you get L-lactic acid in your muscles. And then we have D-lactic acid, and that's found in sour milk. When there's only one enantiomer in a given biological system, which is most often, one of the things to realize is the system can only really use one enantiomer. So humans, for example, use the D isomer of monosaccharides. But they are unable to metabolize the L isomer. D-glucose, for example, tastes really sweet and is nutritious and is a really important part of our diet, but the L isomer is completely tasteless and our body can't use it. Yeast can only ferment D-glucose to produce alcohol. And most animals are only able to utilize L amino acids in the synthesis of proteins. So, humans, animals use D isomers of the carbohydrates, but when we are building our proteins, we use the L amino acids. But the big take-home message here is the reason that this is important and the reason that we're talking about it is because in general, we will only use one of the two enantiomers. And so we have to differentiate between them when we're talking about the synthesis and the use of these biomolecules. So this ends for us our discussion on Fischer projections and the different types of properties of our chiral molecules. As always, if you have any questions, please feel free to stop by my office.